In this lecture, we'll discuss about ECL NOR gate. This is the circuit of our ECL NOR gate in the right hand side of the screen. Now, recall the truth table of OR gate and NOR gate. For OR gate, when both inputs are logic 0, that is, you can see when both inputs are basically logic low, our output will be logic 0, and for all other input combination, our output will be logical 1. For NOR gate, the table will be inverted. That means when all inputs are 0, our output will be logical 1, and for rest of the cases, output will be logical 0. Now we'll verify this truth table from this ECL NOR gate, which might seem quite different from the NOR gate that you are used to know. So the difference between these is there's actually a third transistor here. Side of the input, that is Py. Here is input Py. We have a different third transistor, and the input to this transistor is called the reference voltage. That means the VR is known as the reference voltage, and it is important for a ECL circuit. Now let's assume when both inputs are logical low, what happens? Now our inputs are logical low, but we have a trick, or we have a slight condition, that is how low it should be. It needs to be lower than the reference voltage, because from the previous lecture you need to remember that the ECL circuits work in the active region and cutoff region, and to ensure that the difference between the two inputs have to be greater than 0.12 volt. So this VIL, or this input logical low, has to be at least 0.12 volt less than the VR. So we can write that VIL will be less than VR by at least 0.12 volt. So what will happen if in that case this Q1 and Q2 will be in cutoff? So if Q1 and Q2 in cutoff, our current, there will be no current conducting through these two transistors Q1 and Q2, and our current ICXY will be 0. So we can say that our current ICXY equal to 0, and all the current will flow through this ICR or R2 resistor. So our V01, so what shall be the V01? Since no current will flow through the RC1 resistor, we can say that our output V01 will be V plus, because no voltage drop across the RC1 resistor. And V02 will be something like this. V02 will be, we can write this as V plus minus ICR into RC2. And if this resistance value is a large value, then this V02 will be a quite small value, and we can assign this value to be logical low, and we can write it as VOL2. Here VO output logical low, 2 means for VO2. Now let's consider the second case when the first input is logical high. So we write this as VI high, and the second input is logical low. Now this logical high voltage has to be at least 0.12 volt higher than the reference voltage. So the condition will be now this: VIH is greater than VR, but has to be at least 0.12 volt. In that case, the VIH, for if VIH is logical high, then our Q1 transistors will be on, and Q2 transistor will be off, and the VR transistor will also be in cutoff condition because the Q1 value or Vx has a 0.12, at least 0.12 volt higher than VR. That means no current will flow through this RC2 resistor because QR transistor in cutoff. In that case, we can say the VO2 will be V plus when our both one input is logical high and one other input is logical low. Now what about the value V01? Since all current will now go through the Q1 transistor because Q2 will be in cutoff, but that doesn't change the current flowing through the RC1 resistor. So we can assume the value V01 to be V plus minus, this time it will be ICXY into RC1, and for a moderately high value of RC1, this VO output will be a small value, and we're gonna mark it as VOL1. Now we have VOL1 means the first output's logical low value, and this might not be the same as VOL2. That means the two logical low values for two inputs might not be the same, but we'll try to make them same for our convenience. Now for third case, we are just interchange the input. That means our Vx will be logical low. Let's write this down. And V out VIH, and this is just basically the same as the second case, just symmetric. So we can write this as VOL, then it will be VOL1, and this will be V plus. Now the case 4, when both inputs are logical high. In that case, this is almost the same case because the input of the two transistors BX and Q1 and Q2 are at least 0.12 volt higher than the reference voltage. In that case, the transistor QR will be in cutoff condition and all the current will flow through this Q1 and Q2. So that means the current flowing through the ICR will be 0, and that we can say the VO2 will be V plus because there will be no voltage drop across the RC2 resistor. So we can write this as V plus, and in the same way the output for the V01 will be a logical low, and we can say it will be VOL1, same as the previous case. Now let's compare this output with the truth table we have seen. When all two inputs are 0, our OR gate will have a logical 0 output and NOR gate will have a logical 1 output. And if you compare this to our table we have sent VOL, that means logical low. We are not assuming as 0 volt, but that is logical low. We'll establish the value of these two inputs labels in the next example. Now VIL, when two inputs are logical, we can see the V01, that's the first input, has a logical high and the second input is logical low. And for all other cases, our V1 is logical low and V02 is logical high. So what is the conclusion? We can say that V01 is basically a NOR output and V02 is basically an OR output. So from the same circuit we actually got a NOR gate and OR gate output, and this is one of the advantage of ECL circuits. So we can just write down that V01, that is basically NOR, and V02, that is basically OR gate, and we are getting two different logic circuit outputs from the same logic gate.